Hi everybody, welcome back to the video series for the Crazy Small CPU. In the first video series that you probably watched, we looked at basic CPU architecture. We looked at the components, we looked at combinatorial components and sequential components. We saw that in a CPU there's a section which does the operations on data and the storage of that data, and then we've got a section which controls the data section of the CPU. So I've brought back that diagram of the Crazy Small CPU architecture, but this time I've actually decorated it with some numbers and slashes across the lines, and these slashes indicate a bus. And in CPU and digital logic speak, a bus is a grouping of that many wires. So the number 4 here means that this is a 4-bit data bus, or a 4-bit bus, which is producing 4 electrical signals that come down and get stored in the flags. Now remember last time I said that we've got 4 possible flag outputs: negative, 0, carry and overflow, and so that's why this is a 4-wire bus that joins the output of the ALU down to the flags. So let's quickly have a look at what we've got. We've got an ALU that can only take 2 4-bit inputs, and it can only produce a 4-bit output. Now whenever you say the word 4-bit, you should always think 2 to the power of 4 is 16. So in other words, the numbers can only have 16 possible values. And for this CPU, that means we've got a numeric range of -8 to +7 if we're doing binary arithmetic. Later on we'll see that we can do decimal arithmetic, and so therefore I'm using the decimal numbers 0 to 9. In other words, we've got 1 digit's worth of calculations that we can perform. Any results that the ALU calculates, again, are going to be 4-bit wide. So therefore we can say that this Crazy Small CPU is effectively a 4-bit CPU. RAM locations are going to produce 4 bits of information and store 4 bits of information. But we've got 256 RAM locations we can access. So therefore 2 to the power of 8 is 256. And that means our addresses are 8 bits wide. We need 8 bits of addresses to be able to access those 256 different locations. But of course, if we're going to use an address as a constant, then we can only take 4 of those lines, 4 of those bits to bring in to store in the A and B registers. So out of the 8, we're only ever going to use 4 of those bits to represent constants. Down on the control side of things, we've got 256 instructions that we can have in our programs. So again, we've got an 8-bit address bus, or I should say program counter bus, that allows us to look up 256 different instructions in the address values in the address, and 256 different instructions in the control ROM. Alright, so whenever you see these slashes and numbers printed out on a logic diagram, they're telling you a little bit about the bus sizes, how many wires are going to be moving around. So that also means that if you're going to build this, this is the number of wires you're going to be running between the components. As well as the data buses and the data wires, we also need control lines. So we're going to have 8 bits of information coming out of the control ROM, and that's going to correspond to 1, 2, 3, 4, 5 wires coming out, plus another 3 wires for the ALU operation. So the 8 bits of output from the control ROM will actually become these 1, 2, 3, 4, 5, 6, 7, 8 wires that will spread out like a spider's web out to all of the other components to control. So let's look at how we actually encode instructions. How do we actually get the top 8 bits which with the control lines and the bottom 8 bits which are going to hold the address? So given that we've got 2 ROMs, address and control ROM, and each one is spitting out 8-bit values, you can really think of each instruction as being 16 bits wide. The bottom 8 bits, think of the addresses always being at the bottom, are going to be used to control which location we're accessing in memory. We've got 3 bits for the ALU operation. Now 3 bits normally only means 8 possible operations, but I'm going to steal the multiplexer line, because when we're doing ALU operations, we're probably not going to be using the multiplexer. So therefore 2 to the power of 4 gives us 16 ALU operations. We've got a load line to decide whether to load the A register, and that's an active low signal. So in other words, even though you'll see that A load is being asserted, it actually means we have to drop it down to 0 to actually tell the A register to load. Same thing is true with B load. That has to be active low because the chip that I've used uses active low. We've got RAM write, which again is active low. So if RAM write is 0, that's telling the RAM to load from the data bus. It'll also be telling the ALU to put a value on the data bus, and it'll also be telling the flags register to load the latest value of the flags into the flags register. Okay, so we've got 2 more control lines. PC increments, if it's a low value, the number 0, then it will actually load the address value to jump to a new program counter value. But typically it's going to always be the number 1, and when the program PC increment line is 1, we'll just simply move up to the next program counter value. And finally, the last bit in the instruction is going to control the A cell line. When the A cell line is 0, we will actually take the address from the address ROM and send part of it into the multiplexer so that it may be loaded into the A and B registers. On the other hand, if A cell is 1, then we'll flip the gate on the multiplexer and we'll actually accept the input from the data bus through the multiplexer, and that may be loaded into the A and B registers. Okay, so in this CPU, even though it's a 4-bit CPU in terms of data, the instructions are actually 16 bits wide. Let's have a look at the 16 ALU operations. Now, I did say the ALU has 3 bits coming in, and then we also borrow the A cell line and use it to also as a bit, and that gives us 16 operations. So effectively we've got 2 banks. The bank when A cell is 0 and the bank when A cell is 1. Well, we've got decimal addition and subtraction. That's binary coded decimal addition and subtraction. For those people who want to do binary work, we've got ANDs and ORs and exclusive ORs. We sometimes want to increment a value so that if the A value comes in, we'll simply pass the A plus 1 out on the ALU. I'm going to not talk about B flags right now. I'll come back to that probably in a little bit. But maybe we want to actually just send a 0 out. That's really good if you want to send zeros into RAM. You don't have to load 0 into a register just to send it out, the ALU to put into memory. We can straight away put 0 out the ALU regardless of what's in the A and B input values. Over on the other bank of operations, we've got binary addition, binary subtraction. We might want to pass the output of A out without any regard as to what B's value is. This is useful, for example, if we want to transfer the A's value into the B register, then we will simply output A's value, put it on the data bus, bring it into the multiplexer, and tell B to load the data bus value. So we've got pass A, we've got pass B, that's always very useful as well. And we've got 4 operations that allow us to do multiplication, division, and remainders. Okay, now in a traditional CPU, so that's the one that you're using to watch this video right now, typically every machine cycle will go through a set of phases. And we typically first of all fetch an instruction from memory into the CPU, and we need to store that because it might take us quite a while to run that instruction. So we typically store this into an instruction register. Once we've loaded the instruction, we then have to decode it and work out what that instruction means, because it might actually be quite a complicated instruction. This instruction might actually say, go back and fetch 2 other values of information from memory, do an addition, and once you've got that addition done, store it back in a 3rd position in memory. So in fact, this might actually take multiple micro instructions, multiple tiny instructions to perform. So we often have what are known as macro instructions that have to be decoded, and that causes us to run lots of micro instructions. So the fact that this might be an addition where some of the data has to come out of memory, we might even have to go back in the next phase and fetch that data from memory. Ooh, got a bit of rain going on out there. We might even already have that information in the registers, and that means we don't have to go and fetch data from memory. So let's assume we now have all of the data in our registers. We can now tell the ALU operation what job to perform, and once it's done its job, we can then possibly write the result back to registers, or in fact we might even send it back over the data bus out to RAM. I've just borrowed this picture from computerhope.com. Graphically, the same sort of thing. We fetch instruction from memory, we decode it, we might fetch and perform an operation, and then we might store the results back to memory. And this is what would be done in a traditional CPU. Unfortunately, the Crazy Small CPU isn't traditional. In fact, because it's so minimal, it doesn't really have the concept of an instruction cycle. Effectively, if you know about microcode, then every instruction in the Crazy Small CPU is a micro instruction. So basically, every instruction is simply going to do one small task by sending out control lines to send out to all of those different components and tell each and every one of those to do or not do something. So every time we choose a program counter value, that is sent to the ROMs. We choose an address that might be part of the instruction, and then we certainly choose what control lines and send them out to control various parts of the other components to tell them what to do. So a good example would be these instructions. For example, if we want to load a constant into the A register, well, the address is going to be of the instruction is going to be placed on the address bus anyway. So we simply have to tell A load to load the input from the multiplexer. Now that means A cell is 0, and A cell is 0 will load from that line into the multiplexer. And then of course we need to tell the program counter to increment. So program counter increment, move up to the next instruction. This time let's assume that we want to load from memory into the A register. So we're going to load again, we're going to tell the A register to load. We're definitely going to tell the program counter to move up to the next instruction once we're done. But this time we're going to turn on A cell, make it 1, and that means it will actually load from the data bus. Now this time the RAM is being told which address to access. RAM write is high, RAM write is not being asserted, and so we're going to load that location in memory onto the data bus. A cell is going to cause it to come in through the multiplexer, and A load is going to tell it to load into the A register. Alright, so let's assume we've already got something in the B register. We want to do A plus B, and we want to store that in memory. Well, guess what? This is not a jump instruction, so we will move up to the next instruction at the end of it. We'll tell the ALU to do an add operation. Now, because remember this is combinatorial, as soon as it's being told to add, instantly A plus B is being placed on the output. And in fact, we are telling it to output on the data bus. We're asserting the RAM write control line, and that will tell ALU to output, and it will tell RAM to load, and it will also tell flags to load NVZC. And of course, we've always got an address coming out, so the RAM will know what location in memory that we should be storing the result of the addition. Okay, 2 more instructions to look out. I've already mentioned transfer A to B. We are going to send A through the ALU without looking at the B value. We're going to assert the ALU output on the data bus. We are going to I should actually have A cell turned on in here, because we actually have to tell the multiplexer to load from the data bus, and we're also going to tell B to load what's on the data bus. Alright, so the value of A is going to go through the ALU onto the data bus. The data bus is going to hit the multiplexer, A cell is going to be turned on, and the new value of B is going to be loaded. Now hopefully if you've got your thinking caps on, the fact that we've also turned RAM write on means there's going to be a bit of collateral damage, and as a part of the transfer from A to B will actually overwrite a location in memory. So if you don't specify an address, we'll always treat 255 as the default address, and so therefore in memory, location 255 is a sort of scratch location that typically often gets overwritten by some instructions. Now, finally, if we ever need to jump to a specific address, well then we don't turn on any flags whatsoever. PC increment goes low, and so therefore the program counter will not increment. It will load that address and jump to that next instruction. Okay, so you can see that these are all effectively micro instructions. Every single CSC v2 instruction just sends out a specific set of control lines out to the components and tells each and every one of those to do its job. All right, now I've talked about absolute jumps, so where we tell it to definitely do a jump, but now let's look at conditional jumps, because we might only want to jump to a new instruction based on what's in the flags register. So you can see that the flags value actually comes in to the control and the address ROMs. So we've got the flags values coming in, actually forms part of the address that gets put onto the address ROM and the control ROM, as well as the program counter value. So you know that I already said that we've only got 256 instruction locations. So 2 to the power 8 is 256. Well, that wasn't entirely the entire truth, because in fact we've actually got 4,096 locations for instructions. And that's because at each PC value there are actually 16 different instructions stored based on what the flags value is at that particular point in time. So there isn't a single instruction at a program counter location. In fact, there are 16 instructions. And basically what the control and address ROMs are going to do is choose one of those instructions based on what the program counter value is and what the current set of 4 NZVC flags are. Now, if I just go to the next slide, what you'll see is that from the perspective of the CPU, there's actually a table of instructions. At program counter value 0, we've got 16 possible different instructions in that location. At program counter value 1, again, we've got a different set of 16 instructions. So if you want an instruction to be performed all the time, when we get to a certain program counter value, you've got to put it in at all 16 locations. And the assembler is going to do this for you. If you just say load constant 2 into the A register, then that LCA instruction is going to be placed at all 16 locations at that program counter value. On the other hand, if you want to do a conditional instruction, for example, if you want to say, well, go on to the next instruction if the carry is clear, but on the other hand, jump to location 20 if the carry is set, then what you'll do is, for all of those locations where the carry bit is on, so that's uppercase, you'll put a jump instruction. Okay, there's a jump instruction, and they'll all be jump to that particular new program counter value. And for all of the locations at that program counter value, those 16 instructions, you'll put NOP instructions, no operation instructions. And it doesn't matter what address you put in, because it'll never get used. So if I go back to the next slide, here's a jump if carry is set instruction. So when carry is clear, we do nothing. When carry is set, we jump. When carry is clear, we do nothing. If carry is set, we'll jump. So let's take as an example that the last ALU operation calculated a 0 and stored it somewhere, and the flag's value is 0 and everything else is turned off. Okay, so if we now jump down to do jump if carry is set, we will look up only this instruction for program counter value 0. And we'll see that currently it's doing no operation. So we'll simply increment the PC value down to 1, which means that when we, and of course that won't affect the flags value, so that means we'll also move straight down, and this will be the next instruction that gets performed. So what that means is, as long as the flags don't change, in other words, if we don't do an ALU operation, we don't do a RAM write, or if we do, but the flags values don't change, then we end up having a vertical thread of instructions through ROMs at that particular set of flags values. So let's go back to here. Let's assume that we have a 0 flag value. We'll do nothing. We'll move to program counter 1. Let's assume that we load the number, I'm just trying to think of quickly what I can look at. Let's assume that we load the number 5 into the B register. Well, we will go down to PC value 2, but now we have a value, load the value 5 into the B register won't be an ALU operation, and so therefore we'll stay in this column because the flags value will still be 0. Now this time let's do a transfer A to B. Alright, so let's assume that we loaded A with the number 5. Now we know that the A value is going to be positive and no longer 0. So if we come down to here, this is definitely an ALU operation because we're writing out to the data bus. So we will move the number 5 from the A to the B register, but in doing so, the 0 flag is going to be changed. And in fact, it's actually going to be not negative, not 0, and the number 5 certainly fits into 4 bits. So when we move to program counter value 3, we will actually come down and perform that instruction out of the set of 16 that live at program counter value 3. So we call this idea two-dimensional instructions. And a shout out right now to Chris Baird, who came up with the term 2D instructions and convinced me to put it into the assembler, and by doing so actually has made the crazy small CPU much more sophisticated, and it can do much more powerful things than I ever dreamed that it would be able to do. So let's actually have a look at this in operation. So let's assume that in RAM location 10 you've got a 4-bit value, 0 to 9, or A to F if you think of it in hexadecimal, and you actually want to print this out in ASCII. Now ASCII values are 8-bit, so for example, if I want to print out 0 as a digit, I've actually got to convert that to 30 hexadecimal. If I want to print out the number 9, I've actually got to convert that to 39. If I want to print out something which we consider to be hexadecimal A, the number 10 decimal, then I've actually got to look up and translate that to 41 in 8-bit hexadecimal. Now there is an instruction in the crazy small CPU called the DAB instruction, which displays ASCII by taking the upper 4 bits to be A and the lower 4 bits to come from the B register. So in other words, if I have the number 0 in location, say for example location 10, I've actually got to load 3 into the A register, I've got to load 0 into the B register before I get down to the DAB instruction. And now I want to be able to do this for any of the 16 possible values that we can fit into 4 bits. So let's see how we're going to do this. So these 7 instructions make this happen. And these are a great example of this two-dimensional instruction that we can do in the crazy small CPU. So we're going to start by clearing the carry because we're just about to do an addition. We're going to load constant 7 into the A register. Now why 7? I'll explain that in just a little bit. We're going to load the number 10 we're going to load from RAM location 10. So let's assume that RAM location 10 we have the number 3. Okay, now the number 3 eventually will have to be converted to 33. Okay. Now that I've got the number 3 in the B register, I'm going to add 7 to it with the add and store it into the B register. So B is going to be B plus 7. Not only is it going to be B plus 7, but we're going to set the -0 overflow and carry flags. Okay, well 3 plus 7 is 10. Now that means it's negative, but there was no carry, and it's certainly not a 0 number. Okay, so let's move down to the next line. we've actually got 2 instructions on this line. Remember that there are actually 16 instructions at each program counter value. This is saying, by default, we would normally do load the number 10 back into the B register, load memory location 10 back into the B register. But maybe if the carry was set and the 0 bit was not set, so in other words, this is a positive number that didn't fit into 4 bits, we do nothing. Now, in fact, we know that we did 7 plus 3 is the number 10, so we would actually go back and load the number 3 back into the B register. We would load the number 3 into the constant 3 into the A register, so now we have 3 and 3. So now when we dab, we will actually print out the ASCII value 33, which of course is the ASCII character 3. Excellent, but now let's try out, let's put the number 11 in location 10. And we want to print out the number 11, which is going to be hexadecimal B. So now we actually have to print out 42, hexadecimal 42 as the ASCII value. Okay, we're going to come in and clear the carry. We're going to load a constant 7 into the A register. We're going to fetch the number 11 out of RAM at location 10 and put it into the B register. And now we're going to add 11 plus 7 and put it back into the B register. Okay, so now this will explain why we've got the number 7. Okay, so what's 7 plus 11? That's 18. All right, so 18 certainly will not fit into a 4-bit register. What will actually happen is it'll turn into the number 2. 16 plus 2 is 18. The number 2 will go back in the B register, and the carry bit will be set to say, if you ever do any more addition, then you should add 1 in the next column. All right, so we'll now fall down to this instruction because the number 2 is not 0, but there was a carry on the previous ALU operation. All right, we won't reload the number 11. In fact, we'll stick with the number 2 in the B register and we'll do absolutely nothing. And given that that does nothing, we'll fall down and do this instruction. We will then load the constant 4 into the A register. So now what have we got? We've got the number 2 in the B register. We've got the number 4 in the A register. That corresponds to the next ASCII character after 41, which is the letter B. And in fact, the number 11 is the ASCII letter B. So when we do the dab instruction, B will be printed out instead of a number like 0 to 9. Okay, so this is a good example of the 2D instruction operations that we can do. Once we've got a flags value, we can then decide to go through this thread of operations, or we can go through a different thread of operations. You just have to watch out, because every time you do something that may affect the flags value, then you've got to think about, if I was traversing down through this thread, maybe I'll have jumped with the flags value to a different combination, and that will cause me to look up a different column in the 16 that are at each particular program counter value. Okay, I think that's the end of my presentation. So now, if you're still interested in this, you should watch the next set of videos where we actually start building this crazy small CPU on a breadboard. At the same time, you might want to go and learn a little bit more about the architecture of the CPU. So go back to the description on YouTube and look up the URLs and go out and read the details and possibly download the simulator and try writing some assembly language programs and get them to work. But if you really do want to learn how to build this on your own breadboard, then keep watching, because in the next few videos we'll actually build it from scratch. And as we go through each build phase, I'll test it to show each section working.